Yeah, good afternoon, everybody. Today I am going to do a primer on diffusion models. There is a lot of mathematics in the paper that I sent you guys. I won't be going through all of it because I think that takes away from the main sort of idea behind diffusion models. A lot of it is kind of how you can compute diffusion models in closed form, which just helps with the training process. So it's more about if I skip over some of the mathematics, that means that it's not super, I mean, we can go over it if we have extra time, but I would say that the main goal should be to understand and take away from what kind of diffusion models are and how it relates to Langevin dynamics. So first, let's start with kind of the first figure basically in the paper almost, which is talking about a directed graphical model. So diffusion models kind of have a forward and a reverse process. And the forward process is going from x0, which is our initial data point, and like a Markov chain kind of noising the image more and more by adding a Gaussian distribution in this case. I have another example with different types of distributions because this works for multiple noise distributions. But for natural images, a Gaussian noise distribution is kind of the standard. And then we do this process until we go to xt, big T, and we basically have a noise image, basically. And this kind of relates to other generative models we've been talking about. For example, the way you can think about this in terms of a VAE is that instead of having an encoder sort of predict a posterior distribution or like a prior, we now have xt, which is also a Gaussian distribution, but it's created from the original image. So it's by just, this is also kind of like Langevin dynamics is like, or Langevin dynamics we use to recover the original image. But what you should take away from this is we get an original image, we keep adding noise to it recursively, and big T will be something in the range of 1,000. So it's a lot of steps.
Do you measure Gaussianity and then you stop when it's Gaussian enough?
No, they just take a T.
Go far enough. So.
Yeah, and you have like a few hyperparameters that you can take in terms of like how much Gaussian noise you add. But the main idea is kind of, at some point, it'll just be noise. And T at 1,000 seems to be kind of a good indicator of it being noise. And you can imagine that for a variational autoencoder, we use an encoder to create sort of a distribution, then we sample from it. In this case, we don't use an encoder, but we constantly recursively add noise to the original image, and we get a latent variable that is as big in dimensionality as the original image. But it's kind of the same. You can see it as like we start with Z kind of, except Z we created through like adding noise to it recursively. And then we sort of have a normal distribution, if that makes sense.
Sounds like random walk.
Yeah, kind of, yeah.
In that M 8 megabit dimensional space.
Yeah. So yeah, the reverse process is kind of like a decoder, but it's based on Langevin dynamics, because Langevin dynamics is basically the idea that you can recover the noise recursively back and subtract that from the image. So recursive, this is a Markov chain both ways around. Okay, I'll show you. So these are a few examples. So the first row is the forward process that I just talked about, which is adding noise. So we go from T0, which is the original input, and we recursively add noise until we get to T, big T. And then it's a, yeah.
So the spiral is an image or a trajectory?
No, the spiral is just the sort of, it's the, what's the data set called? It's like a specific Swiss data set, I think.
But is it
what two-dimensional data sets?
So we're looking at this image of that spiral, and
well, yeah, this is just the whole data set plotted, basically.
Is it a single point, right? And then you're adding noise to those points.
Let me see. I can just,
It's not like a first point is in the middle of the spiral. Second point is spiraling out. That's how I interpreted it when I was looking at it.
so what it says is the proposed modeling framework trained on the 2D Swiss roll data. So this is the 2D Swiss roll data.
So it's an image, two-dimensional image in a sense.
Well, this is the whole data, I think. So each point gets added with noise, and then the whole data set will look like what I'm showing you in the right image. T is big T.
So if you go back to the image example, it is like the human face on the left.
One point in the Swiss roll, I think, is like an image in that other data set.
Yeah, exactly. So this is the whole data set. So basically you can say like at T is T, the whole data set is kind of sampled from a Gaussian distribution. Because it's,
So why the first one does look like,
that's the Swiss, that's
Inspire.
just the data set.
okay,
That's just the input data set. This is just a Swiss roll. It's like a toy data set that we sometimes use because it's nice because you can't linearly.
so it is the collection of all the samples.
Yeah.
in the-
And so you can see that basically as T is big T, it's almost like all those samples are sampled from a normal distribution. That makes sense. Like if you go all the way to the right, it just looks like you are sampling like a lot of points from a normal distribution. And you create those points by adding noise to it more and more and more. And then the reverse process is we have a Gaussian distribution on the right, and we try to recover recursively the original data. And that's actually the model they're trained. So P x of 0 until T, that's their model predicting back sort of. So you sample, let's say we have 10,000 points on the right, the red, the middle part. You have 10,000 points. So you sample 10,000 points from a normal distribution, and then recursively, big T steps, we can recover the original data by recursively predicting the noise and subtracting that from the image. And that subtraction is shown below. So it's going to recursively predict the noise and subtract that from the data point. And then when you do that T times, you kind of go back to the original data.
With the same prediction function, with the same probability, or different for each step.
I think that's a good question. Let me just check in there for sure. I think it's just one.
The transition probability is the same, that's what I'm asking. Or like in the forward process, Q is the same
I think, yeah, I think
at
for
each step.
Yeah, I think for each step it'll be the same. Okay. So you can see kind of the dynamics arising slowly throughout the process, the reverse process, which is the bottom row. It'll slowly start being able to recover the original data set. Because that's the difference you take between the predicted. So F mu of xt comma t minus xt, that function predicts the noise. And so what they do now is, so normally you would take xt minus that function because the function predicts the noise in xt. But now you take the opposite to show kind of what noise it's predicting. So where it's predicting noise. So black would be where it's thinking it's noise, and white is where it's thinking it's not noise, which is the original data distribution. This is another example. So these two examples are from a different paper because I thought these examples were just a good way of visualizing it first. So the original data is on the left, and what they're showing is like the generated samples, but they're identical to the training data. So that's kind of the training data. They give us input, the right one, with the first row being all ones, I guess, and plus noise, plus a lot of binomial noise, because this is a binomial example. And then over time, it is able to remove kind of that noise from the input, which is noise. And you'll see that, well, they say that it's identical to the training data when you get to t to 0. That's kind of the idea. So you create a very noisy version of an image, and then you recursively try to recover the original image back. Yeah. So how does this relate to other generative models? I took this from a blog, which I would suggest if you want to learn more about this to read, because it's a very good combination, sort of aggregation of multiple papers about this. So like I kind of said before, you can see that what we're doing here is we're basically creating Z not through an encoder, but by a Markov chain that gradually adds Gaussian noise. And then we try to reverse it. So it's kind of this combination between flow-based models in a way, because we're trying to, the Z is going to be as big as the dimensionality of the data, although some flow-based models have smaller dimensionality, but the original ones like NICE have the same dimensionality as the data. And then we try to recursively map it back to the original image. And Z in this case, for natural images, will be the Gaussian distribution, because we recursively add Gaussian noise. Now we're getting into the mathematics. Okay, I split it up a little differently, so they talk about
sorry to this. Before that, can you go back and explain again, like why it's different from all the other forms? I think I missed.
Right. So I mean, with the
main
VAE,
part.
with the VAE, for example, we are predicting. We parameterize Z, which is sort of the prior distribution that the posterior distribution that we think the data came from, using an encoder. But we're not doing that here.
Well, Q is your encoder. In the you can say Q is your encoder.
It's kind of like an encoder, but it's different in the way. Well, so you can parameterize these, like gradually adding Gaussian noises, but they don't do that. So it's a set sort of variance that you add to the model. So like it's a very general description. You can make it as general as you want, but they notice that like it's better if you just have a sort of set parameters. So yes, in a way it is an encoder, but instead of like predicting a lower dimensional manifold posterior, the data dimensionality stays the same. And it's a sort of, it's more like an autoregressive process where you assume a Markov chain and you sequentially, you recursively add noise. Now the fact that Gaussian, you can, so the reason, part of the reason why they use a Gaussian distribution is because you can in closed form calculate X some T from X0. You don't actually have to recursively do something to get like a noise image at time T. You can do that in closed form. They explain in the paper the mathematics of that. But in closed form, you can add noise to X0. That will be the same as if you have recursively added it T times. So that makes it easier to train, because if you would have to recursively do everything, then it would be really hard. You would be very manually intensive.
Yeah, that answers the question. Thanks.
Okay, so just real quick, how they train this is they randomly sample a T for, that's smaller than between 0 and big T, and they predict the previous one. And because you can compute both of them, xt minus 1 and xt in closed form, you're kind of training to predict every T over the time of your training span if you take a uniform distribution.
Don't you want to go backwards in one step as well?
No, so that's not what they're training, because that's the Langevin dynamics part, where it's like you kind of try to non-linearly. It would be optimal if you could do it in one step, but it's more like an autoregressive process where you you predict the noise from an image to take it back one step. And so sampling is pretty intensive. Takes a long time to sample images if you just have the noise distribution.
Okay, I'll think about it as you go.
So the Langevin dynamics part is the fact that you do it sequentially. I mean, yeah, the best way would be to just be able to predict back the original image, but I think the way they set the problem is using the dynamics.
You said it in both ways as dynamics, and in the forward, you just multiply your Gaussians through.
Yeah.
And why couldn't you multiply whatever parameter parameterization of P you're using as well.
I think that this is probably more stable, that's why they're doing it, but I know that it's not the forward thing, so adding the noise can be done in closed form, and the backward, the reverse process has to be done in steps. So the first of all, the forward process looks like this, where you recursively multiply xt minus 1 with you predict xt using xt minus 1, which is this is the joint distribution of those sort of noisy samples, and the way you do that is using a normal distribution, where the Gaussian noise of the data is done according to a variance schedule, beta 1 until beta t, and you can, if you wanted to, parameterize these, but they don't parameterize these. So it's all very generally stated in the paper, but that's also why I kind of skip over some of the mathematics, because they say like this would be the general form, but we don't use the general form because it's too complex and it doesn't work as well, and so we use the simpler form. But this is kind of how it works. So you predict xt based on a sort of variance added to xt minus 1, where you can see that the mean part here is the square root of this beta t, 1 minus beta t times xt minus 1, and the variance part is just the beta t. And you do this recursively, but you can also compute this in closed form.
What is the intuition behind this choice of variances? Specifically, this, like, it's diagonal covariance, but also the data is scaled.
Yeah, it's a diagonal covariance.
But did they explain why that scaling of the data, 1 over square root of 1 minus beta?
If we remove the scaling, it's just a random walk random walk. But now instead of random walk, you make a step, then retract by square root of 1 minus b every time. That's an interesting observation. But for betas, Rogers, I don't know if you looked at the paper, but betas, they go from small to large. So the further you are, the larger the noise, the variance.
Yeah.
They're further from x0 because they're going in both directions.
Yeah. But so in their paper, they say the forward process variances beta t can be learned by reparametrization or held constant as hyperparameters. So, and I think they keep them constant during training.
Yeah, that's what they say, 0.01, like they start with 1,000s and go to 1.
Yeah, exactly.
Divide 1 by 1,000.
I
So
was
this-
just asking because it's counterintuitive. When you scale the data by a number, you're already sort of setting the variance or the scaling the standard deviation the same way. So I'm just confused why you need to do that to the data.
Why do you
Not
say
embedded in the
scaling?
covariance.
What do you mean by scaling the data? Who scales the data?
So xt minus 1 is the data from the previous step, and it's multiplied by a constant.
It's a sample. Think of a random walk. It's your next step.
Yeah, so x0 would be the data, but then x1 is sampled from this distribution. And then you multiply it by the square root of 1 minus beta t, and then you sample it to get x2, and you go further and further. So only x0 is the actual data, but once you go further and further, it's just a sample from a normal distribution that you parameterize like this.
Okay, thank you for the clarification, but I think I realize what the issue is. I'm confusing. Beta is in the covariance matrix is the variance of xt, whereas the square root of 1 minus beta is a scaling on xt minus 1. So it's different things being scaled differently. Yeah.
Yeah, but this is Rogers. This is a legitimate question, I think, because I'm also now confused. But the thing I think what they're doing, you have you start with a Gaussian centered at your image, x0. And then you make a random step from that center, basically, spherically equiprobable step. And you're probably, depending on dimension, will be in some ring. And then instead of moving this whole Gaussian with progressively expanding beta t sigma variance, instead of moving it over there, you're scaling it back to the center, to that image by, no, to the origin, I guess, by doing square root of 1 minus beta. So you are scaling, but in a sense, you're retracting towards the origin. I don't know why, instead of like retracting towards the original image. So you stay close to it.
Because you want to end up with a Gaussian centered at 0 with 1.
Oh, okay. So you're equivalent. Okay. So you're pushing the variance to 1.
Yeah.
Okay. Yeah,
And you're
that's a good one.
and you're
And you're
pushing
pushing the mean
zero.
to 0.
Because
That's-
then you get kind of the same prior that you have on variational autoencoders, which is a 0 mean, 1 standard deviation that is fully diagonal.
So it's a schedule, basically. It's a
Yeah.
deterministic trajectory that pushes you to
Yeah.
variance 1.
To the
mean
prior
to
that you
0.
have, because that's why they say you can parameterize this as you want. You could say it's a mean 1, but then you just choose a different schedule for beta t.
For, well, different normalization factor or whatever.
exactly. I mean, yeah, but I mean, like, in terms of like the fact that it is a schedule.
Well, this is like a Gaussian process in a sense, but like it's a function of x, so you can choose whatever mean function of and whatever variance function.
Right.
Okay.
So this is the first step, and you can compute this in closed form, is what they're saying. I'll talk about that in a bit. Then the reverse process, which is what we're kind of mostly interested in, is to compute this joint distribution, where instead of going higher in t, we go kind of back. So we're trying to predict the previous t. We're trying to predict t minus 1, basically. And how you can formulate this is predicting the mean and the variance using xt. And this looks very much like how a variational autoencoder is also described, because mu theta can be a neural network parameterized with parameters theta, and sigma theta can be a neural network as well. And that's very similar to the encoder of a variational autoencoder. They're not doing it exactly like this because they kind of state everything, but this is the main sort of idea behind it. So from xt minus 1, which is a sample from a normal distribution, we try to predict the sample before it, using, in this case, parameterized by a neural network. And I think you can see here that they don't use a different neural network per step, because the mu theta only depends on the data, so not on t. It does take t as an input, but it doesn't depend on t.
A quick question.
Yeah.
Why did you call it an encoder and not a decoder?
I mean, okay, so the reason why I compare it to an encoder for a variational autoencoder is because you predict the mu and variance, the mu and the sigma. I mean, yes, this is a decoder, but it looks a lot like the way you parameterize the encoder of a variational autoencoder, if that makes sense.
You mean that the output of this network are the mean and the
Oh,
covariance?
okay, so the way you do the encoder for a variational autoencoder is that you try to predict a posterior distribution, and you parameterize that posterior distribution using a neural network that predicts mu theta and a neural network that predicts sigma theta. So in that way, it looks similar, except in this way, they're not trying to predict the posterior, but they're trying to decode the original image. So you're right that this is actually a decoder, but the parameterization looks a lot like how you would parameterize the encoder of a variational autoencoder, like the posterior that you're predicting with the encoder.
Yeah, I think I got the idea. I still just don't understand the dimensions of the output. If it's estimating the parameters, mu and sigma, or if it's estimating as the output the previous sample.
No, so it's predicting mu and sigma. And then you sample from that to get xt minus 1.
All right, got it.
And the training is actually performed using the same idea as the variational autoencoder, namely the variational bound on the negative log likelihood. And this looks very complex. But what it's basically saying is we have the log probability of the noise, the final noise thing, and a lot of KL divergences. Because if you look at this, you can see that it's P theta divided by Q of X, and this is a KL divergence. You can write this in terms of KL divergences. And
Well, your sum is expectation over P. I
yeah,
guess.
exactly, yeah. And so that's why you can create a KL divergences. That's also what they do. And this is their training. This is their general training formula, which is the KL divergence between the predicted, the forward process, because xt here is the forward process, this Q is the forward process, and the prior that we have. So in that case, in this case, it would be the zero mean 1 standard deviation. So, and if you parameterize beta t, sorry. If you parameterize beta t, then this will be important in the loss as well. But because in their paper they say they keep beta t constant and it's not learnable, you can drop this term from the equation. But what this is really saying is that the forward process, when you finish t amount of steps, in this case 1,000, it should be similar to the prior that we have. So zero mean 1 standard deviation. This part of the loss is saying that we want to have that the forward process t minus 1 given xt and x0 should be similar to the reverse process, namely predicting xt minus 1 given xt, and that's the sum over p bigger than 1. And we have the final, which is kind of the prediction of x0 given our second to last final step. So it's like the before we encode the original data again. That's L0, which is going to be the log likelihood instead of the KL divergence, to make it similar to other generative models. So now you can calculate the negative log likelihood of your data distribution using that last term.
And just quick recap, the parameters of the Gaussian that you're learning are fixed, right? They're the same for all.
For the forward process. For the forward process, yes.
What do you call forward process?
The forward process is
Q.
creating noise. Yeah, it's noising it. Yeah, so that's Q. So this term falls away because this is not learnable Q in this case. So this is their most general way of describing the sort of loss function. But because in their paper they say, hey, we're not actually going to make Q learnable, this part of the loss falls away, so we don't use it. And then in this case, the Q here is fixed. So the distribution is fixed. So you're just trying to create P theta closer to the Q distribution that you create, which is fixed. You can make both learnable. So if you go back to the forward process, if you make these variance schedule, if we make it learnable, then we were talking about the fact that it wants to go towards the mean 0 and standard deviation 1. If you make beta 1 until t learnable, you can get you can make it so that it goes more and more towards that 0 mean 1 standard deviation. But because we're not making it learnable, it doesn't make sense to optimize this loss because it's not going to learn anything.
In KL divergence, second term, LT minus one, L sub T minus one.
Yeah.
The integral, the KL divergence is with respect to Q, expectations with respect to Q, right?
Yeah.
Yeah. So P
Can I-
theta,
Yeah, go ahead.
No, I can't wait for a second.
yeah, just a quick comment question. P theta is basically trying to capture as much of the Q as possible.
It's trying to
The way it's
capture,
written.
it's trying to capture the generation of xt minus one, how much Q knows about xt minus one given x and x zero, xt and x zero. So it's just one step, but because it's a sum, you're right. You're basically trying to do everything.
I'm just trying to interpret KL divergence because it's not P over Q, but Q over P. It kind of, yeah, okay, anyways, okay. Roger, see your turn, sorry.
So what I'm trying to get to here is P of theta is the same no matter T, right? No matter
Yeah.
which T I choose, it's the same.
Yeah.
So it's one network that works on all these transitions. One time.
It is not a network, Rogers, it's Gaussian, remember the mu, it's a Gaussian parameterized by two functions, mu and sigma.
Yeah.
Like a
Right,
Gaussian.
but there is a network that learns that theta
Yeah,
and
exactly.
that sigma.
Yeah.
That's what I'm talking about.
Yeah.
So yes, the outputs are the thetas or the parameters, but it's the same for every pair of time points.
The output is not theta, but the output is mu and sigma,
He gets that.
parameterized by theta.
Why isn't mu and sigma the same as theta?
But because theta are the parameters that you use to transform the previous image into mu and into theta, and into sigma, sorry.
Neural network parameters.
Yeah, neural network parameters.
Oh, sure. Yes.
I mean, it's just
Got it,
semantic.
yes.
It's just a little,
Mhm. Okay, sorry for that confusion. Sure, it's the network parameters.
yeah, it's, yeah. Okay. So yeah, there's a lot of mathematics in between here, and I'll try to explain parts of it that are interesting. But so they basically say, okay, this is our general, this is our general, what we want to optimize, but we don't have to, because we can do a much simpler thing to optimize. And this looks much more like Langevin dynamics, like more clearly like Langevin dynamics. And I'll go through each of the variables because we haven't talked about them before. So first of all, we're doing the norm, we're doing the expectancy over T, x0, which is the data, so every data sample, and epsilon, which is a sample from a normal distribution. And they optimize the squared norm between the noise and the noise predicted by our network, given x0 and t, where a of t is the closed form of the forward process that we have. So AT will be the noise added to x0 in closed form. So this part of the equation, this will be xt here, because we can calculate it in closed form, which is like this.
But what is equal to xt?
So again, so I'll maybe just open the paper to explain this a little bit further. It's annoying because it's a lot of mathematics that kind of makes it harder to understand this part. So what we can do is, here, this is the important part. A notable property of the forward process is that it emits sampling xt at an arbitrary time step t in closed form, using the notation at equals 1 minus beta t, and then at with a bar is just the sort of like the joint probability of each of those AS's, each of those ATs. So then, instead of writing this recursive here, which I showed before, this recursive process, we can just sample xt in the forward process directly from x0.
So isn't it easier to say that the equation on the left of the highlighted one is a product of Gaussians, and product
Yeah.
of Gaussians is a Gaussian,
Yeah, exactly.
and we know the parameter of mu and sigma of that Gaussian.
Yeah.
So we just sample from that Gaussian
Exactly.
directly
Yeah.
because we can compute it
Exactly.
analytically.
So, but that's where this, I'll just go down. This is a lot of the stuff that we're.
Yeah, I was confused with why do you call square root of alpha bar t times x0 and you called it x1
xt.
or xt.
Yeah, so because that's kind of how they interpret it, because you can compute, so if you go back here to this equation, this is the same as getting xt from x0.
You have to sample to get it.
Right, exactly, but the reason why they don't do sampling directly is because they use the reparameterization trick, which is why we have that epsilon thing. Because what you can do, that's also using a variational autoencoder, is you can do, let's open the wrapper.
Oh,
I think
okay.
maybe a better way of saying it is that it's not x of t, it's the mean of x of t.
No, it is x, okay, so you're right that it is the mean of x of t, but the terms together, these terms together, this is x of t here.
Before comma.
Yeah, before the comma of t. This is x of t. And
Yeah. So you're sampling from Gaussian.
Yeah.
Everyone knows how.
Yeah, the epsilon is a sample, right?
yeah,
Yeah.
exactly.
You're sampling
Yeah, I'm
from
just, because of how much notation there is, I just want to make sure that it's clear.
So I still have some issue with intuition here.
Mhm.
The my confusion is with the mu and sigma that we're estimating and the relationship to the statistics or the parameters of Q. What's the relationship between the two?
Not of Q, of P, right? Or are you asking about Q? The Q is
I
fixed.
think I'm asking about Q. It's the forward one, right?
Yeah, the
Yeah.
forward. Yeah.
And mu and sigma are for the backward process, P.
Yes.
Isn't there a relationship between the two, or shouldn't there be? And if not, why not?
Well, so the relationship is that we're trying to model is this, right? We're trying to,
I read that as try to make them the same,
yeah,
but then we already know the answer because we know Q.
It isn't, if I understand correctly, isn't the point that you're trying to learn the parameters that create these Qs? Because that's what gives you the like a generative model.
no, I mean, okay, so what they say is they try to learn the underlying density of the data distribution by being able to reconstruct, so by being able to predict what is noise, indirectly, you're learning the data density of the data distribution.
Can you look at this P theta in the K divergence LT sub 1? Did they mess up the direction? Oh no, okay. So in Q, so Q samples from the past to the future. P samples from the future to the past. So
Yeah.
P is correct here. It goes from xt to xt minus 1. But Q doesn't know how to go back. Q goes forward. Why did they write backward here?
No, but I think, yeah, so I'll go back to the paper. I also noticed that.
Q should go forward. So.
No, I agree. I think there's a reason for that.
And that's kind of, I'm trying to answer also Rogers, your question, because P goes in a different direction.
Yeah, it looks weird because here they have the correct Q
Yeah,
direction.
this is correct.
So what they say here is the forward process to the constant and expression of the rear is ensured in part by the choice of Gaussian conditionals. And this, yeah, it looks to me like a mistake, maybe, I can maybe look here, if they change something here. This is the block, by the way.
Let's actually copy.
They also took the exact same. Yeah, that's a good question. Oh, here.
Like if we already know the backward process, why do we need P? That's and they call it forward process. Oh, but that's forward process plus T there.
Yeah,
They are inverting it. Okay.
where mu of t is this. So that's like the.
So they can
I think that
analytically.
determines my question. Yeah.
Oh, wait, I think I know what they're
Estimating a
doing.
posterior, not.
What
Yeah,
they're-
yeah.
Right.
What they're doing is sampling xt minus 1 and xt from x0, and then you can condition it on each other, I think. Because-
No, they can do the number six, they can write it down because they know the likelihood. They know what the q of x t minus one.
Right, but here, this is the mu of t minus 1, which they can get from x0, because it's in closed form. And they can get, this is kind of, I think this is the reverse that they're trying to do here.
They need to apply Bayesian probability inversion formula to get xt minus one given xt.
Yeah.
Because all they have is xt given xt minus one. They do have that.
Right, and they have x0 now, that's why they add x0 to make it tractable.
Yeah, but then they need prior on xt and x0, and they need normalization factor by xt minus one. To apply Bayesian. So it looks like 6 will work out analytically if you have analytical form of this 3, which all of them will be Gaussian. Dividing by Gaussian is the same as multiplying by Gaussian.
Let's see if I can make it more clear here. Yeah, so they use, this is what they do. They use Bayes' rule as follows. Where they can get xt minus 1 given xt comma x0 using xt given xt minus 1 and x0, which is just a forward process.
Yeah, that explains it.
Exactly. And that's what they're optimizing. So they're trying to make these two distributions as similar as possible. Which makes sense, because in effect, what they're doing is trying to minimize the difference between the inverted Gaussian and this neural network that's trying
But
to.
why do that? I mean, I already have it. I inverted it. Bayes helped me. I already have my.
Right, true. But
Yeah, exactly.
why do I
That
need
was my
P?
follow-up.
Yeah, why would I need P?
okay, but so if you minimize those two, what they're saying is you're learning the underlying data distribution, the underlying density of the data distribution.
But I mean, are you learning that?
Well, I mean, that's why they were able to publish the paper, because apparently they do.
Well, so the point that I'm trying to make is you have P, which gives you the parameters as
Mhm.
the output.
Yes.
Then you will sample from that. Is that going to give you the image?
So, okay, let's say we
That the idea?
give it random noise. So we just take our prior, which is 0 mean standard deviation. We sample a point from that. Or actually we sample the whole image of points, because that's what they're doing. So let's say 28 by 28, if it's MNIST. Our neural network can recursively go back and recursively reconstruct an image that would, so it's unconditional image generation then, because you can generate back the original data. That's what they're doing here as well. So you sample a bunch of points, and then recursively peak data is going to predict each t minus 1 from t until you come back to p0, which is going to be the original data. Is that what you mean? So I can show you an image of what they do for images. Here. I don't know if this helps. I mean, for me, it's also hard. I think it's also really hard paper. I had like a lot of midterms this week, so I had to read this pretty quickly. But so they start with this sort of like this sample that they sample from a Gaussian. I guess it's 64 by 64 or something.
I think my point is that the network, network is not outputting the image at each time point. It's outputting the parameters. So you need to sample.
Yeah.
And then apply the network again and sample, and you keep going back in time
Yeah.
until the t times and you get the final.
Yeah, but that's what I was saying, right?
But the point I think that I was asking is, we know the distribution already, so we can do that with the closed form solution distribution. We know the posterior without having to optimize, without even a network.
Yeah, but then you can also say we also know the original input image, x0. So why would we even need a neural network to generate it?
No, but posterior is computed. I agree with Rogers. What will happen if we use Q inverted Q? They're cheating us by calling it the same Q, but it's a different.
Okay, but so
distribution.
you can't do unconditional image generation then. That's the problem. You can't generate new points if you just use the exact inverse, the analytical inverse. Because there's no like,
Right, just add, generate another noise and just apply this posterior. Why not? What will happen then?
So, I mean, what you're describing is very similar to deconvolution, right? If you convolve with a bunch of Gaussian kernels and then deconvolve, correlate them, you should get back to the original image or something similar to it, but it might actually be that good, right?
I think it's not comparable because
Yeah,
it's not
I
in
don't think
data
it's
space.
in the same category at all.
This is estimating parameters, and then you sample from the distribution.
Yeah, no, that's what I'm saying. Like, you can do this unparameterized, but I don't think that would be a very good model.
Q is parameterized. You just estimate those parameters.
Q
by-
is or P?
no, Q is not parameterized.
Yeah.
That's
It's
why.
parameterized by betas.
Yeah, but the
But
betas
those
are
are-
constant, so
yeah, those
it's
are-
not
that's
learning
fine.
at
You
all.
compute them when you invert Q, when you do. This Q in 6 should be called something else. It's not Q anymore.
But then I don't understand how it's not similar to what he's saying. Isn't that exactly what you're doing? You're just keeping the constants the same for a Gaussian kernel, and then you're doing deconvolution with the same Gaussian kernel. Yeah, I mean, you get,
I computed posterior distribution. It's a different function now.
yeah, using.
I
Gaussian
learned
kernels.
it from data.
Yeah, using, I mean, you're not.
I learned
learning
it from data.
No, you're not learning anything, because they're set. Beta T is set. It's just a constant. It's
No, but
what you're
my
learning-
my equation 6, if you notice, mu depends on xt and x0.
Yeah, but it's not learned. It's set. It's, what you're doing is just sampling recursively.
Okay, Rogers, I think I know what they mean. Because mu depends on x0, we want to get rid of that dependence. The only reason, otherwise we have the optimal solution.
Yeah,
Mu depends on x0c. The posterior for each of the transitions will depend on the ground truth, which we don't want to depend on. So you want to fit p sub theta to this mu such that it's there,
yeah.
but it's not
Mhm.
using x0. So that's why you're parameterizing. You're kind of smoothing implicitly or something x0. You're faking x0.
but here what they're doing is they're almost exactly sampling xt minus 1, because this a bar t minus 1 is going to be the sort of the closed form joint probability of the Gaussians until t minus 1.
When we will minimize 5 to 0, we will be doing that too.
Yeah,
We
exactly.
want to do that.
Yeah, exactly.
That's
Yeah.
what confused me and Rogers, is because
Okay.
that's the optimum. That's what you want to do.
Right, but that's why I said like, it's the same as just having the original image. I mean, yeah.
Well, I mean, you have it there, the highlighted part. That is the crux of the problem. You don't want to have it there, but you want to have, you
Right,
want to
I
be
think-
as close as possible to this, but without having X0.
Right, and so the reason why they have it is because it's intractable. It becomes tractable when you condition it on X0. But it's intractable if you don't, which is exactly, like you said, the problem. That's why we're trying to do a neural network to parameterize the intractable distribution. Or at least the Bayes rule is intractable, I guess. Without X0.
Well, intractable in the sense that we don't know Q of xt and we don't know Q of xt minus 1, or we
Right.
can't know that in those distributions.
I agree with that.
Can I say one last thing?
Yeah.
It seems then that you could call this a VAE where you're learning the posterior, the parameters of the posterior.
Right, so I agree with that, but I think that's, you can call that generative models kind of in general. That's what they're all kind of trying to do.
VAE is a special case
Yeah.
of something else
Yeah.
as well.
But I agree, so that's why I try to kind of do the comparison with VAEs, because there's a lot of similarities. Even in the bound they're optimizing is the same as the bound for VAEs, except they have a sum over all the Markov chain samples they create in the forward process. And this part is sort of like the Langevin dynamics. Because so you have noise and you subtract sort of what they're saying is kind of like the learned gradient of the data density. And that's kind of the relation to Langevin dynamics, is that you use the sort of a gradient of the data density, and if you subtract that from the noise if you subtract that from the noise long enough, you get the original data back. And this is
Why
their
is
training.
that a function of X0 still? Shouldn't it go away?
Yeah, but this is what, let me see. Yeah, okay, the reason why it's dependent on X0 is because you're doing the forward process and predicting, so this is just the forward process until T. But we want to predict XT minus 1, and in our previous, what I just showed you on we want XT minus 1 to not be dependent on X0. So I mean, what they're saying here is this is just a sampled XT, because it's the mu of XT plus the variance times a sample from a normal distribution.
Okay.
And we're trying to predict XT minus 1, but XT minus 1 shouldn't predict on X0. If that makes sense. Like the whole problem that we just had, that we just described.
Well, we figured it out, yeah.
Yeah, here the problem is that we don't want to have to predict XT minus 0 using X0. That's the thing. But the forward process is, I mean, with the forward process, you use X0 to get XT. It's just that predicting XT minus 1 shouldn't depend on X0.
Okay. Mhm.
Cool. This is their training algorithm. You first sample your X0, which is just from your data distribution, from the data you have. Then you take a uniform T between 1 and T, big T. You sample this E parameter from a normal distribution, and then you take these gradient descent steps. So the closed, like at this point, it looks pretty simple. There's a lot of mathematics that went before this, and a lot of assumptions and a lot of putting things to constants. But in the end, it turns out to be a fairly simple gradient update, where this part, like I just said, resembles the sampling of XT using the forward process, and this is a neural network that predicts the data, the data distribution, the density of the data distribution. Okay,
And T is an actual index.
I don't know if they use it.
Like, what is epsilon sub theta is a network, as you said.
Yeah,
So
yeah.
it takes two parameters.
T and
like a vector and a skip type one?
That part I don't know for sure. I think they maybe do that, because what you probably will get if you use just one neural network and you don't tell it which T in the Markov chain you're at, it becomes a little cumbersome in terms of predicting things, because
So
you.
then we need some kind of like a positional
Yeah,
encoding
so
rather
probably-
than
exactly,
a
yeah.
number.
I think they use a positional encoding,
So
but
it's more of a like sigma shock, just to give us something to think
a
about.
little extra hit.
Is it
Just-
like what you're saying? Is it the same as thinking of T as which samples in the batch or in the mini batch?
What do you mean?
I was wondering if T, small t, represents samples in the mini batch.
No,
Because you're taking
small,
randomly.
It's time index.
small team is the time index for how many forward process steps you've taken.
Yeah, but that's all fixed and a bit.
No,
No,
Sampling
because
is
small t is sampled from the uniform distribution.
Step 3.
That's what I mean. You're picking a random time point.
Yeah, but
And
it's just
that's-
helping the neural network learn this distribution, because the distribution should be a little different per time step. Because when you have big T, it's just a zero mean, one standard deviation Gaussian distribution. But when you get close to 1, it has to be able to predict, when it gets 1, it has to predict the original data point x0. So it's a little like the
But-
predictions will be different over time, I think.
Let me flip the question and ask it differently. What are the elements in the observations inside your mini batch? Different images or different time points in the same image?
Yeah, XTs, so different XTs. So you sample, okay, let's say it's a mini batch, right? T will be, let's say our mini batch is 64. You'll sample 64 Ts. You'll apply the forward process to 64 X0s.
Yeah, okay, that's what I thought then. Okay, we're on the same
So
page.
you train on one image.
I don't know if you train on one image. I think you can do different based on what you want to do. I think what they probably do is they just take a mini batch of X0s, 64. They sample 64 different Ts, and then they do a gradient update on that. But it may also be more stable if you just take 64 Ts and one X0 and apply 64 different Ts. I think that's more like training dynamics. I mostly try to understand their mathematical description because it's a lot.
Yeah.
And then sampling is just taking X big T from a normal distribution that's 0 and 1 standard deviation mean. And then for each T in T, big T into 1, you just start doing this process recursively until you end up with X0, where this is also sampled from a normal distribution. So it's kind of like the reparameterization trick again with a neural network, but then recursively. Some results. So here, this is big T, and we go to 0 on the right. And they show you different images from in between. So this is pretty cool, I think. You can clearly see that it kind of starts recovering high definition things at the end, and it starts with more like general things, more abstract things on the left. This is conditional sampling. So if we create this noise based on a certain image, forward process for 1,000 steps, these are the images we can create back by sampling them. But as we have less forward steps, the data is going to look more and more like the original data point that we put in to the forward process. That makes sense. So like this is just very noisy, so you don't get data that looks a lot like the initial input image, but because this is the initial input image. But as we take less and less forward steps as the input to the sort of decoder, we start to get the original image back. And you can see that it's pretty cool that it can generate multiple sort of different types of the same data as it gets closer.
So I wonder why when they show, we need a new standard, when they show results on the left, they should show the closest image to this one from the training set.
I agree, yeah, that would be good. And they can also do interpolations. Where if you take a source and something you want to you can do interpolation of the Geenjaar basically, where these are kind of their results. What they just do is they take they sample from they sample their original data point, and they sample their xt, which through the forward process, and then they can decode the linear interpolated latent between the two original x zeros like this. So they create a new xt in the forward process by using this lambda basically. Yeah, and then they reverse the process using the decoder. That's it. Do you have any questions?
So
Okay.
the dimensionality of the latent space is huge. And if you add too much noise, you kind of lose something.
Well, you lose the original image. So you can see, for example, after 1,000 steps, it won't decode the original data anymore, because the original data is this. So the further back you go, the more you go towards the posterior. But if you only take 500 steps, it's kind of like conditioning on an image, because you're only halfway through the Markov chain.
So can I say that the takeaway is don't do this, don't add too much noise, otherwise you lose. You're not
Well, I
able
mean,
to
if you
recover.
want to obtain the original posterior distribution, you do want to add a lot of noise. But the less noise you add, the
Okay, so
more
you're saying that you
condition-
generalize better if you
Yeah,
add
exactly.
more noise. Okay.
But you can condition it by just doing less steps in the forward process, because it's going to be more and more, because you predict xt minus 1 from xt, the more xt looks like the original x0, the more so the path is carved out for the network to predict for, if that makes sense.
Is that, could you say that that's related to fine tuning?
Fine tuning of what?
Like if you want to do, if you have a very general network trained on large data with this approach, then for fine tuning on your data set, you would not train it with a lot of noise. You would use less noise. Is that reasonable?
Yeah, you could say that maybe, yeah.
But let's say I missed something. You want your final step to be something that is purely noise, right?
Yeah.
Purely Gaussian. But you said you could kind of use fewer steps.
Well, okay, so the idea is your training algorithm, you are trying to get the posterior. You're trying to, but of course, the more steps you take, the more it looks like the actual posterior, because it's going to be fully noise, zero mean, one standard deviation. But if you take less steps, it's going to look more and more like the original data point that you put in. And in that way, you're kind of conditioning it on that point. On the data.
But I thought the idea of this whole thing is this way you can generate from just random noise. But
Right.
if you cut it off at fewer steps.
The reason why they add this is because generative models generally show a few sets of results. Unconditional image generation, which is from the noise, conditional sampling results, because they just want to compare it to other generative models. With VAEs, you can add your sort of Y, which is your target variable, and condition your posterior that you predict with your encoder from Y and from X. And then you can do conditional image generation. That's just why they add this result, because intuitively you can kind of do conditional sampling, although the original goal of the paper is to get this posterior that is very high quality.
Okay, and all these other models don't do that very well.
Well, actually, they say that the results are not as good as the other models, but they're better than, for example, energy-based models. But it's also very new. Like this is very, very like the original. I think one of the first papers on this was published in like 2015, but like only the last 2 years this has been like really coming of age and like becoming more and more important.
I think Harsh found the
In what
paper-
sense are they not? Sorry, I was asking if in what sense are they not as good as other models?
The negative log likelihood on the test set.
What does that say?
So, I mean, flow-based models, for example, are better at the negative log likelihood, like predicting the original data. So, yeah, I mean, it's just this term in their loss function, basically. This part is on the test set. This is not as good as flow-based models, for example. But it's very close, and the whole point is kind of like flow-based models have been developed for a few years now, like 2 or 3 years, and this is pretty new. So there's still a lot to gain, and even though it's not the best result, it's a very interesting way of looking at the problem, and there's a lot more to do. Because there's actually an OpenAI paper in 2021 that does get state-of-the-art negative log likelihood on a lot of data. So it came out this year, and it's even better, and it's even cooler, and now it has surpassed the other models. But I thought this one was more complete, this paper, together with the other paper that I showed you and the log.
Out of curiosity, what did they say about the dimensionality of the latent space being so high?
But
Their
that's
inspection
actually not considered a bad thing. So for flow-based models, especially the initial ones, the nonlinear, nice, they also have a latent space that's as big as the original data.
Okay, we're out of time, way out of time, 10 minutes, but that was an interesting talk and a good explanation. Thank you, Eloy. I learned a lot.
Yeah, thank you.
One thing I wanted to add is the only problem, and that's being solved in the 2021 paper by OpenAI, is the sampling process, because you need to do 1,000 steps to sample. So 1,000 passes through a neural network. And I saw that for 100 images, 32 by 32, it takes 2 days or something to generate. And so the OpenAI paper has kind of solved that by making it more efficient.
Do they change the sampling process, or do they just
Yeah,
make it more
Yeah,
efficient?
I mean, I didn't want to get into it because it's like even deeper, but like, yeah, they changed the sampling process a bit.
I'll take a guess that I think it might be related to something I saw on using, like, differentiating through ordinary differential equation solver. That maybe there's some connection to that, like casting the problem in that way, casting the dynamics and as a differential equation. And being
You mean
able
the
to solve
note
it.
paper?
I couldn't say. It was a talk I saw a while back. Didn't keep track, so
Yeah, Amrit
it's a guess.
spoke on that. You're talking about this series, then Amrit spoke about it 2 years ago, a year and a half. But anyways, yeah. Okay, thank you, everyone. I'm stopping the recording.